Wonderful. Can everybody hear me? Okay. Okay, and you can see my screen, right? Wonderful. So today we're finishing our next to last module. And quite frankly, our next module is going to be very short, just one class period. Otherwise, we would not be able to fit all the student presentations. So today I want to talk about using mass spectrometry to look at higher order structure and interactions of biomolecules. And I want to start with some perhaps trivial considerations that well, perhaps not trivial, but something that is not so sophisticated as shown on the slide. So the idea is that you want to find out what interaction partners a certain protein or any other biopolymer has. And so what you can do, you can use it as a bait. You have to attach some affinity tag to it. So you would put this conjugate into a system. It could be tissue, it could be cell culture. In some experiments, it could be even a living organism. And then you would isolate the complex. So 1, 2, 3, 4, and so forth. All these ovals on this diagram indicate various other biopolymers that interact with your bait. And then you use affinity tag to separate this complex on the column. Then you would use standard methods to dissociate all these pieces that are bound to your bait. Perhaps use SDS page to separate them out based on their molecular weight, as we discussed in the separations module in this class. And then every individual band can be cut from the gel, and you would redissolve these proteins or whatever biopolymers these ovals represent in solution, and use mass spec in order to find their molecular weight, their sequence, and so that way you would be able to identify them. So this is a pretty straightforward approach. I think I used an unfortunate choice of words in the beginning. This is by no means trivial. This is technically, this is very sophisticated, very involved experiment. It's just the idea is very straightforward, right? But the way you implement it is not that's easy. So it requires a lot of technical skill and very significant investment of both time and money, both to plan out this work as well as to execute it correctly. So, but the idea is pretty straightforward. And what's lacking here, it only allows you to identify interacting partners for your protein or whatever your bait is. And it does not really tell you much about this interaction. Stoichiometry, affinity, epitopes, and so forth. So all these things are beyond the scope of this measurement. And fortunately, mass spectrometry offers several other ways to look at higher order biomolecular structure, including very large protein complexes. And in many cases, that allows you to really deduce very detailed information about this high order structure of biopolymers that is frequently unavailable from other sources, right? And so before I begin this discussion, I want to show this, my next slide. And the reason I want to show it is that very frequently mass spectrometrists are criticized by physical community for attempting to characterize high order structure of biopolymers in the gas phase. And so the idea is that the argument is that once you remove your biopolymer from its native environment, which is aqueous environment for the most part, right? So that should change its biophysical characteristics very significantly. And particularly in the past, I think now most people are convinced that mass spectrometry can deliver valid view of biopolymer interaction, high order structure, even though you do carry out your measurements in the gas phase, not in solution. But in the past, it was a very significant concern. And quite frankly, whenever you are attempting to use mass spectrometry for this purpose, let's say you're trying to understand how a multi-unit protein is assembled, or how protein A interacts with protein B, and so forth. You always need to keep in mind that because the environment in which the measurements are made is very different from the native environment, there is always a possibility that you would introduce some experimental error, right? And so a few things that you need to consider are this. So let's say you have a biopolymer assembly and you pull it from solution into gas phase, or it's actually vacuum. So it's very low, it has very low pressure there. So there is no solvent anymore. And so the question that you need to ask yourself is, how does that affect the stability of high order structures, stability of all these non-covalent complexes, and so forth. And a few things to consider is, so a very important thing is that you really need to put in perspective the biomolecular interaction in general, and remember that it is made of several things, several interactions. And so the most important of them are listed here. So that's electrostatic interaction. So typically in biophysics, we refer to that as salt bridges and so forth, right? Then there are hydrogen bonds. So hydrogen bonds are distinct from electrostatic interactions. And then, of course, there are hydrophobic interactions. So fortunately, when you pull a biopolymer from its native environment into the gas phase, you are not really doing anything bad as far as electrostatic interactions or hydrogen bonds. In fact, hydrogen bonds would become stronger because now there is no solvent. Solvent is aqueous solvent. Obviously, that's polar environment. And so there is always a competition between internal hydrogen bond formation and external hydrogen bond formation with the molecules of water, right? So now water is no longer around. And so whatever hydrogen bonds you had that were stabilizing your structure in solution, now they are even stronger, just because there is no competition anymore. Same is true about electrostatic interactions. Remember, electrostatic interactions are strong, but in polar solutions, such as water, there is dielectric constant. So in water, dielectric constant is what? Almost 81, right? So which means that the attraction between two charges, once you move them from vacuum to water, it's reduced by 2 orders of magnitude, almost 2 orders of magnitude. So, and therefore, whatever salt bridges you had in the gas phase, they would be much stronger because there is no this screening effect of this dielectric medium that you have in the native environment. So these two things actually benefit from transition from the native environment to the gas phase. So the only thing that you are definitely losing when you go to the vacuum is the hydrophobic interactions. So by the very definition, once water disappears, there is no hydrophobic interaction anymore, right? There would be very weak van der Waals interaction, and that's it. And so this is important. So these 3 lines are important to consider when you are weighing pros and cons of making certain measurements in the gas phase. So if your system is such that it's primarily stabilized by hydrophobic interactions, then there is a very good chance that your measurements are going to fail, right? But if you have a significant component contributed by electrostatic interactions and by hydrogen bonds, then there is a very good chance that you will you're going to do well in the gas phase. All right. Okay. So for some reason, okay, my screen doesn't want to work. So before it died completely, let me go to my next slide. And so on my next slide, I have an amino acid sequence of a small, hold on one second. Do you see any glitches on your screens?
No, not really.
Okay, so it's probably just me. Okay, give me 1 second. I think I would be a lousy IT specialist, just to put it mildly. All right, so it looks good again. So on this slide, I have a regular mass spectrum of a protein. This is ferritin. So ferritin is, for those of you who took biochemistry recently, you probably remember, this is iron storage depot that our cells are using to keep iron, mineralized iron. So of course, iron under aerobic conditions is not soluble, so its bioavailability is very close to zero, and we need a lot of that. And so ferritin serves the role of storing iron until the cell needs it. So anyway, it's a fairly small protein, a typical mass spectrum shown in the middle of this diagram. So you see these multiple peaks corresponding to the same protein, but different charge states. So they cover a pretty large M/Z region. Of course, with this protein, we can do MSMS measurements. So this is something that we talked about previously. So you can get the sequence of this protein. But an interesting thing that we haven't discussed so far, and I want to show it now, is that if you go again to the level of the intact protein, and you decide to reacquire this spectrum shown here, but now instead of using denaturing conditions, which we typically use in mass spec, so it would be water methanol or water acetonitrile mixture with a little bit of either acetic acid or formic acid added. So now, if instead of that, you try to use solvent that is a better representation of the native environment. I'm not saying this is native solvent, because remember, in electrospray ionization, unfortunately, we cannot use non-volatile buffers. We cannot use non-volatile salts, but we can still make a wise selection of components for our solution, and we can maintain physiological pH, physiological ionic strength, and so forth. And if we do that, the mass spectrum that we would acquire would look very different. Okay. And so the mass, if you were to deconvolute this mass spectrum, so you would suddenly recognize that the mass that you're measuring is 24 times higher than what you measured before. And the reason for that is that ferritin in the native environment is not a single protein. It's an assembly, it's a hollow sphere, as shown in the lower left corner of my slide. It's a hollow sphere made of 24 identical subunits. So I highlighted in blue one of them, but it's there are 23 others. And so they actually make this hollow sphere, which and mineralized iron is stored inside the sphere, right? So in this particular case, we're dealing with the so-called apoprotein, so there is no iron inside. And so what you measure is just the mass of the protein content. 24 mass units. 24 subunits, exactly, not 23, not 25. And so this is really wonderful news to us, because what it tells us is that you can look at quaternary assembly, pretty large quaternary assembly of proteins, right? And perhaps you can even go beyond that, and you can look at the interaction of different proteins. So one other thing that I also wanted to highlight here is look at the extent of the multiple charging. So when we looked at the mass spectrum acquired under denaturing conditions, the average number of charges was somewhere between 19 and 20, right? For just one single subunit. You go to 24 subunits, and now you have it's a high number of charges, but unlike mass, the charge is not multiplied by 24, right? It's a fairly modest increase in the extent of multiple charging when you compare it to the mass increase, right? So you have less than 3-fold increase in charge and 24-fold increase in mass. And of course, the reason for that is that the extent in electrospray ionization, the extent of multiple charging is a reflection of your protein conformation in solution. In this case, when we use denaturing conditions, the protein was random coil, right? So its solvent exposed surface area was very large. And this is exactly what allowed it to accommodate so many charges in the process of electrospray ionization. Here, we are making our measurements under near native conditions. So the protein is fairly compact. All units are folded, and they are assembled in this large quaternary structure, right? And so that gives you much less, the room to put charges is much smaller, okay? And so therefore, you're not seeing the extent of the increase of extent of multiple charging that would be congruent to the increase in mass, right? So, and this is what I want to highlight and discuss in the next few slides. It turns out it gives us a wonderful ability to look at protein conformations in solution, even when you work with a single chain protein. And so my next example would be transferrin, another iron related protein. So this is iron transport protein in our blood. And as you can see, I have 3 different spectra of the same protein here. The one at the top was acquired at neutral pH. So this is very close to physiological pH. This is mildly acidic pH. And this is obviously very highly denaturing environment. So I have alcohol there, and I have significant amount of acetic acid. And you can see that in all cases, I have multiply charged species representing the same protein. It's a single chain protein. So if I were to calculate the mass, it would be the same mass for all 3 spectra. But look at how the charging patterns differ from one another as you go from top to the bottom. So here, under native, or I should be careful, I should call it near native conditions. Under near native conditions, we have very few charges, and the charge density is low, right? It's plus 20 is the average charge. And the reason for that is that the protein is folded. And so when I transfer it from the gas phase, from solution to the gas phase, I cannot put too many charges on its surface, right? It's folded. In this case, in the other extreme, the protein is unfolded. In solution, it's random coil. And that allows me to put many charges on its surface as I pull it from solution to the gas phase. And so now we go from plus 20 to plus 15 average, right? That's a huge change. And here in the intermediate case, this is probably the most interesting case because we clearly see bimodal charge state distribution. So a very significant fraction of our protein apparently still maintains native or near native fold, right? So it does not denature. So this distribution is very similar to the distribution we've seen at pH 4. But then we also see a very wide distribution of charges ranging from somewhere like plus 50 all the way down to plus 20. And so these are partially unfolded species. So what happens at this intermediate pH, the protein just begins to feel unhappy, right? And a fraction of protein molecules begin to unfold. So this is most likely a reversible process. So they spend some time in the unfolded state, then they would refold back. But the stability of this folded conformation now is compromised. And therefore, you see this partially unfolded species under these conditions. Okay, so this phenomenon has been observed and rationalized fairly long time ago, nearly 25 years ago, and it now is used very commonly, routinely, I would say, as a means to evaluate conformational dynamics of protein under a variety of conditions. Again, one caveat here is that you cannot make these measurements under truly physiological conditions, right? You're restricted to volatile systems. So you cannot use sodium chloride, you cannot use phosphate buffers and so forth in your system. But even with those limitations, this is a very, very useful tool when it comes to detection and visualization of protein dynamic events. All right, I think I should skip my next slide and I will go to an example of how this is used in biopharmaceutical industry, for example. So in the previous slide, in the case of transferrin, we induced protein unfolding ourselves by changing the protein environment, right? So what the biopharma is interested in more is looking at various modifications of the protein and trying to understand how they affect the stability of the high order structure of the protein. So for biopharma, this is a very important consideration because once the protein unfolds, obviously it would not be able to carry out its function, right? So you're losing the activity for at least a fraction of your protein molecules. But even more serious concern is that by virtue of unfolding of the protein, you expose certain neoepitopes, parts of the protein that our immune system does not see under native conditions. And so once it begins to see them, it would recognize them as foreign objects, as invaders. And then the patient's immune system would be able to develop the immune response to that, right? So this is, unfortunately, it happened in the past. Perhaps the most dramatic example of that was the fiasco of EPO. I think it was, you guys are probably too young to remember that. So it was the end of 2000s, right before 2010. So there is a protein called erythropoietin. So what it does, it stimulates production of red blood cells, and it's administered to people who have compromised ability to do this by themselves, particular people emerging after chemotherapy, people, patients who have very low red blood cell counts, so they are prescribed EPO. And so unfortunately what happened, so it was more than 10 years ago, it was a real crisis because all of a sudden the company, and I'm not going to name the company, those of you who are interested, I can give you some reading on that subject. So what the company did, they just changed the formulation apparently without realizing that. So somehow it affected the conformation of the protein. So And as a result was a massive development of immune response. And this is really tragic because you are giving this therapeutic peptide was given to patients who did not produce enough red blood cells, right? And so now instead of helping them, you're actually eliciting immune response that begins to silence all the activity related to, so it neutralizes the various proteins that are designed to increase the red blood cell count. And so that was a really a very significant health crisis that affected a very large number of people, both here in the United States, but even more in Europe. And eventually it was resolved. It was really a trivial reason behind all this. So apparently the new filling used the syringes with the stoppers that were not covered. So it was just resin, and somehow the protein, when it would come in contact with this resin, would change its conformation, and that was enough to trigger the immune response. So anyway, I'm saying all this just to emphasize that this is a very huge concern. It's not just some academic exercise, you know, can I see conformational change here or there? This is a very serious concern in biopharma. And when you do a new drug application for a biologic drug, or when you are developing a follow-on version of an existing biotherapeutic protein, you always have to prove that there are no conformational changes now. So this is different from small molecules. We don't have this issue with small molecule drugs. It's unique to macromolecular drugs. So anyway, the example that is shown here is another biotherapeutic. So this is interferon beta 1A. It's used for many different things, but this particular formulation was used as treatment for multiple sclerosis under the trade name of Avonex. And so this is a fairly small protein, and an interesting thing about it is that it has odd number of disulfide, all odd number of cysteine residues. So there are 3 of them. 2 of them form this disulfide bridge here, but 1 of them is unpaired. And it had been viewed as both the source of trouble and an opportunity. So there was a company, a European drug maker, Serono. I think they have been consumed by somebody else since then. So they decided to modify this protein and to increase its lifetime in circulation by adding polyethylene glycol chain here. So this is kind of a natural conjugation site for a PEG chain. Small protein, the problem with a small protein is that its lifetime in circulation is very short, because it can be cleared through kidneys. And that is a really bad news for patients, because administration of this, this is intramuscular administration, it's very painful. So there are a lot of issues, a lot of patient compliance issues with interferon beta 1A. So in fact, I had the chance to talk to one patient, and she shared with me how really painful it is. So it's, I mean, pain lasts several days after the IM injection. And then there is a psychological effect. So the person begins to really feel bad a week before the injection, just because she knew that what was coming. So it really is a serious concern. And the idea was just to pegylate the protein. So PEG is chemically and biologically inert. So it would not really destroy any physiological properties of this protein. But the only thing that it would do, it would increase its radius of gyration, so it would not be cleared through kidney very quickly. So the trouble here is that this cysteine is located in the alpha helix, and so when they actually tried to do that, they failed. So it was a program which eventually had to be terminated, and a very costly program. And I think the data that I'm going to show you on this slide gives us some clues as to why it happened. And so this is a mass spectrum. Shown in blue is the mass spectrum of interferon beta 1A. So this is the biologic product taken under neonative conditions. And you can see that this is a typical mass spectrum. Well, the only atypical thing is the presence of some heterogeneity. So these peaks correspond to minor glycoforms of this protein. You see that it's a glycoprotein. It has one sugar polysaccharide chain. But otherwise, it's a typical mass spectrum, electrospray mass spectrum, multiple charges. So this is the deconvoluted mass spectrum of this protein. And so the number of charges is fairly low, right? So this is the average charge is 9. So the protein is happy. Now, what happens if you modify this protein, not even with the PEG chain, but just with a very small chemical group? So in this case, we are looking at NEM, and we attach it to, of course, it's reactive towards cysteine. So it's a very minor chemical modification, right? And the result of this modification, you can clearly see it in the convoluted spectrum. There is a mass shift. So there is incorporation of exactly one NEM group covalently into this protein. But you also begin to see something else if you look at the raw mass spectrum. Now there is additional distribution of ion peaks that show up at lower M/Z values. So these guys have high charge density. It's the same mass, but different number of charges. And as we have discussed before, what it tells us is that this is a fraction of proteins that at this particular moment are unhappy. So they lost their native fold, and therefore the surface accessible area becomes larger, so they can accommodate a significantly larger number of charges on their surface as they go from solution to the gas phase. So clearly, even a very simple experiment that takes literally a few minutes to complete would tell you that it's not a very good idea to use the cysteine as a pegylation site, and probably save the company a lot of money. Okay, and just for reference, this is a fully denatured protein. When you run it under denaturing conditions, the spectrum, the corresponding spectrum is represented with a gray trace here. So the extent of multiple charging is even more significant. However, we can clearly see that chemical conjugation of this protein at this particular site is not a good idea. All right, I will skip my next slide. And I now want to look at something more complex. Up to this point, I was talking about just proteins, but I repeatedly said biopolymers, implying that these ideas can be generalized. And so I want to show it here in this slide. So this is an example of analysis of quaternary structure interactions of NIC-R. So it's regulatory protein from H. pylori. As you guys know, H. pylori is a very peculiar bacterium, right? It lives in stomach in very harsh environments. And it does that by reducing acidity in its immediate environment using a series of enzymes. And so the production of these enzymes is regulated by the protein, which is called NIC-R. So those of you who are interested in the biological background, there is a very nice review published a long time ago, which still is valid. So the protein is, NIC-R is a tetramer. Okay, so I was trying to depict it here using a crystal structure. So a single chain is shown in blue, the rest of the protein is shown in gray, so that's a tetrameric structure. And the peculiar thing is that the activity of this protein is regulated by nickel. So in the presence of nickel, each monomer changes its conformation, and as a result, the entire assembly changes its conformation. So this is what it becomes, right? So now I'm trying to show it in color. And once you have this conformational change, that allows you to bind to DNA segment, right? So this is how it happens. So that's a pretty sophisticated series of events involving multiple partners, metal ion, proteins, and DNA, right? So is it something that mass spectrometry can help us look at? It turns out the answer is yes. And I am trying to illustrate it here using this slide. So the diagram at the top, the black trace, the black trace shows the tetramer of NiCr in the absence of nickel. And the red trace shows the same tetramer, but this spectrum was acquired in the presence of nickel. So the charge state distributions look similar, right? But if you zoom in, you would see that there is a mass shift. And so the mass shift corresponds to the inclusion of 4 nickel atoms into this tetrameric assembly. So we can definitely see that. Now, the next question is, can we see its interaction with DNA? So this is how double-stranded DNA, so here we just have a relatively short double-stranded DNA segment, about 30,000 delta, 30 kilodalton. So if we mix that with both forms of NiCr, we see very significant mass shift here, right? So it's a new distribution. And if you calculate the mass, that would be the mass of the entire complex, both protein and DNA. In this case, the most abundant signal is still protein, right? Unbound protein. There is a little bit of interaction with DNA, but not as significant. Unfortunately, we cannot attach a number to it, right? We cannot quantitate it using mass spectrometry. And this is, by the way, a very significant shortcoming of this technique known as native MS. It is very difficult to obtain quantitative information. You can get a yes or no answer, but you cannot obtain affinity figures. So, but there is definitely some binding. And the reason for this binding is that something that is not obvious from X-ray structure, but there is some residual binding even for this protein conformation. It's much weaker because instead of bidentate binding, you have a monodentate binding now. But nonetheless, you can clearly detect that with mass spec. So this is a really wonderful technique in that regard. So just a few examples that I gave you today. I hope I already mentioned pros and cons. So it's very easy to use, very straightforward way to get answers to many important questions related to protein high order structure. But let me skip that. So this is something that I didn't say much, but this is absolutely true. So quite a few systems, of course, crystallography and NMR would produce much higher resolution pictures. But in terms of how much you need to invest into creating a single crystal for crystallography, also considering the molecular weight limitations of high resolution NMR, I would say 90% of systems that can be addressed using native mass spec, they are unfortunately currently outside of the reach of NMR and crystallography. So definitely mass spec has its own niche there. The cons, well, this is a very important thing. we cannot really say much beyond just what the composition of the non-covalent complex is and what the stoichiometries are, right? So we cannot attain very high level of resolution using this technique. We cannot get, we see unfolding when we look at charge state distributions, but we cannot really say where this unfolding happens, right? And a very important restriction is that we have to use the systems that we say are mimic native environment, right? But in many cases where we absolutely have to have sodium chloride or some other salts buffers that are incompatible with electrospray ionization, unfortunately, we cannot do that. So this is very, very significant shortcoming of mass spectrometry. And of course, membrane proteins, some other difficult systems, they had been significant progress in the past decade, I would say, but it still is not routine type of analysis. So these things are extremely difficult. All right. So how to get around this in the remaining 8 minutes? Well, there are other methods that you can use in conjunction with mass spec detection that would allow you to fix at least some of the shortcomings that I listed on my previous slide. And in this class, we don't have time to talk about all of them. The only thing that I would mention is hydrogen deuterium exchange. Okay, so the idea here is very simple. So let's say you have a protein, and this protein is folded, and when you start when you expose it to deuterium-based buffer solution, you would have exchange on the surface, right? So hydrogen containing groups that are on the surface of the protein would be able to exchange, but everything in the interior would not exchange because there is no solvent access there, right? And so you have to either unfold the protein. In the case of complete unfolding, you would label everything. In the case of partial unfolding, perhaps you would label some parts of the protein. So, but in either case, it gives you the ability to actually quantitate the unfolding processes, determine the extent, and also, as I will try to show in the remaining few slides, you can try to localize these segments of the protein. So how is this done? Well, this is not a trivial thing by any means. Sometimes we try to, make it sound like it's very simple, but it's not. And the problem is that even when you look at proteins, there are several different types of labile hydrogens. So all hydrogens attached to heteroatoms, such as nitrogen, sulfur, oxygen, and so forth, they are exchangeable. Hydrogens that are attached to carbon atoms, they are not exchangeable, right? So, but everything that is shown in blue and maroon and magenta here, these are exchangeable hydrogens. Well, it turns out the exchange with solvent is a very complex chemical process, and it depends on a lot of things such as temperature, solution pH, and so forth, in addition to the protein, in addition to accessibility of these hydrogens. And what's interesting, for every type of hydrogen, the exchange is either acid or base catalyzed, but usually base catalysis is much stronger. And so the kinetic plots, so these are exchange rates for unprotected hydrogens of different types that you see here on this diagram. So they are they have this peculiar shape, right? So each of them has a minimum. So typically, we are interested in carrying out exchange reactions under native conditions. So that would be somewhere here, right? And so for all types of hydrogens, this is pretty fast process. Now, the one type of hydrogen atoms that we are particularly interested in are amide hydrogens. And the reason for that is that they're uniformly distributed across the polypeptide backbone, right? Proline is the only amino acid that doesn't have an amide hydrogen. And so therefore, with the exception of proline, for each residue, we have a single reporter, which is great. And what we do, we take advantage of the fact that the minimum of the exchange rate for these type of hydrogens is between pH 2.5 and 3. And at this level, all other types of hydrogens exchange fairly fast. So to them, this is acid catalyzed part of the curve. So it's only these types of hydrogens that I am pointing arrows to that are significantly decelerated, or as we say, quenched under these conditions. So the exchange is extremely slow. And this is what we use in our experimental schemes. So I will show just one experimental scheme very quickly. So you have a protein in H2O based buffer, right? And then you quickly dilute it to D2O. So the red color here signifies deuterium. Blue is hydrogen 1. So, and as you can see here, all these segments that are unstructured, they begin to exchange, right? And so now your task is to find out what they are in terms of the entire amino acid sequence of the protein. So what you do now, you quench the exchange, right? So you decrease the temperature of your solution to close to 0, and you also put the pH level down to 2.5, 3, right? So you are losing all exchanged hydrogens on the side chains, because under these conditions, the exchange is still acid catalyzed. But the backbone hydrogens are protected, right? They are quenched. And that's all you care about now. You don't care about side chains. You forget about side chains. You only look at the backbone amides. So you quench the exchange. You can quickly dissolve the protein and look at the change in its mass. And so this global exchange would tell you how quickly the protein acquires this isotopic label as a whole. Or you can say, I want to see local information. I want to see where exactly this dynamic regions are located within the protein. And so then you would digest your protein. So fortunately, there is an enzyme called pepsin. So this is something that we use in our stomachs to process food, right? So stomach, as I mentioned before, has very acidic environment. So pepsin is one of the very few enzymes that remains active under acidic conditions. And so you use that to break proteolytically your protein into small pieces. And then you dissolve the species using, let's say, LCMS, and you look at their masses. And so peptide ions that represents protein segments that were involved in secondary structural elements, or perhaps they were sequestered from the solvent in the interior of the protein, you would observe very little exchange with time there. So the isotopic distributions would be pretty much unchanged. But other segments that represent more dynamic regions of the protein, you would see a very significant incorporation of deuterium label. Okay, so this is how you do these measurements. And I ran out of time, but I just want to show, I want to make connection to one of the slides that I had before. So remember, we talked about interferon beta 1A and how it's not a good idea to put NEM functionality on this free cysteine, right? So we've seen just by looking at charge state distributions that protein begins to feel unhappy, but we couldn't really tell what exactly happened to the protein. So this question can be answered using mass spec, so NHD exchange. So here, there is if you do HD exchange, you would observe that there is a group of peptic fragments underlined in red, that seem to be located far away from the cysteine in question, right? So this is the cysteine that we are conjugating to NEM. So, but we see a lot of dynamics, a lot of difference in dynamics between intact and conjugated version of the protein in this particular region. So, specifically, if you look at the intact protein and over a period of 2 minutes, there is very little change in the isotopic distribution. So very little incorporation of deuterium. But if you look at the same peptide derived from conjugated protein, that's red trace, you see that even after 10 seconds, we begin to see very significant deuterium uptake, right? So this is definitely, now it becomes a very dynamic part of the protein. And the reason for that is that this segment is highlighted in my structure in blue here. And in 3D, it faces, so two helices make a bundle, and it faces, this helix faces this cysteine residue. So once you put a bulky NEM functionality on the cysteine, it would become much more difficult for you to keep this helix intact. And you clearly see that in dramatic acceleration of the deuterium uptake. Okay. So with that, I will finish my today's presentation. Just a few, a very quick announcement. Since we fell behind the schedule, and I was supposed to finish the mass spec module last Friday, but it's only today that we are finally done with mass spec. I will put the homework on Canvas today. And so therefore, you will still have 2 full weeks to complete it, right? So, and you will see that it's right on the front page of the homework. So it will be due 2 weeks from now. If you need extra time, please let Max know. So now it's, you know, holiday season, some people are traveling, there are some other things. We will be very accommodating and very understanding. So if you need more time, just let us know. We will absolutely do that. And as always, I think it worked well last time that we had this involved homework, number 1. If you have any issues, instead of just copying the answers from your classmates, talk to Max, okay? So this will have 0 reflection on your grade, right? But he will be able to put you on the right path, and our goal is to learn as much as possible and give you some practical skills, right? So this homework would be much more like homework number 1. So you would have to deal with some practical problem. Not as difficult, maybe. I think homework 1 was too difficult for some people. So this one should be much easier. All right. One other thing, we are beginning Friday, we'll start our student presentations. So I think I already mentioned that. I will say it again. What I want to see in your presentation is a short segment where you give the physical and chemical foundation of the technique that you are presenting, right? Such that we would allow, it should allow us to understand how it works, right? At least one example would be wonderful. A practical example of how it's applied to a specific problem. And ideally, we also want to see some, perhaps not a discussion, you are limited, you don't have much time, but at the very least, you need to list the pros and cons of this technique, right? Particularly compared to what we looked at in the classroom during this semester, okay? So, but the most important criterion is that you should be excited about that. If it's interesting to you, it will be interesting to us. If you feel bored to death, I don't think you would be able to excite us. Okay, so that's the main criterion. All right, so with that, I will stay here for a few more minutes if you have questions, but those of you who need to go for other classes, please do so. And let me stop recording.
Thank you.
Thank you, Professor.
You're
Thank you,
welcome.
Professor.